In the last class, we were discussing about this inspection of gears, right? So, as the name implies, inspection of the gear means uh, some people they may call it as gear testing, gear checking, or gear analysis, right? Basically, it is to inspect the manufactured gear in the production line. Once the gear is being manufactured, they need to be inspected before it is be accepted or rejected. So for those gear inspections, generally the gear inspection can be classified into two broad categories. One is functional inspection, another one is analytical inspection. The functional inspection, as the name represent, functional, whether the gear which is being manufactured under the process will it be functioned or not. Whatever the reason behind which the gear is being manufactured, whether it is going to function properly or not. Will it function with respect to the desired requirements or not? That is what the functional inspection is about, right? So generally, this will be used along with the other gear, so that they need to check the functionality of the particular gear. That is the functional inspection. Another category of the inspection is analytical inspection. See, analytical inspection means it is also called elemental gear inspection. So as we discussed in the last class, elements for a particular gear, it consists of so many different elements, and those elements, individual element, it need to be inspected. So that's why analytical inspection can also be referred as elemental gear inspection. It can be the lead profile, the pitch, the runout, the concentricity of the particular gear which is being manufactured. Those individual elements will be manufactured under this particular category. That is analytical gear inspection. And in between these two, analytical gear inspection is the one which is used for the inspecting of the gear usually, right? Because as you can see over here, the last point, the advantage of this analytical inspection is that it allows the user to quick and easily identify the elements of the gear which is falling out of the tolerance, whether the pitch, whether the concentricity, whether the lead for the given gear, or the profile of the gear. Those elements they can able to individually and quickly they can able to analyze it. They can inspect it whether it is falling out of the tolerance zone or not, right? And this information is very much essential for the manufacturing process in order to control it. If you want to control something, you need to measure it, and you need to measure it. For these gear inspection, there are a lot of different types of measuring instruments, measuring gauges will be used, right? So this was what we discussed in the last class. Again, particularly with respect to the spur gear measurement, the analytical inspection, or it is also referred to as elemental inspection. So elements, these are the following some of the elements of the gears, like runout, pitch, profile, lead, backlash, tooth thickness, concentricity, right? So these are some of the individual elements which will be inspected in order to control the manufacturing process of the gears, right? So we'll discuss one by one. So this was the gear runout. So run out means the amount of the gear move in and out with respect to the true center is concerned. That is, it is about the eccentricity of the pitch circle. That is what gear runout represent. Whenever it tend to be eccentric, whenever the gear tend to be eccentric, you tend to have the vibration. Eccentricity means it is moving in and out of the true center. You can observe in this image eccentric gear. This is the true center, but it is rotating or moving in and out with respect to some other center. It leads to vibration. The more this type of the more the eccentricity in the particular gear plank, the more the vibration, and finally it may lead to abrupt gear failures. In order to avoid that failure during the usage in the machines, it need to be inspected at the production plant itself, during that manufacturing plant itself, before it is sent to the assembly with the any other mechanical elements, right? So that is what the gear run out, to check how much is the eccentricity is there, what whether the gear blank is rotating, how much with the vibration, in and out with the true center. So in order to inspect that, they will be using one of the simple device for this, which is having the dial indicator with the ball or the cylinder type of plunger in it, right? Each gear, tooth by tooth, it will be rotated one by one, and any deviations or any variations which is indicated in the dial indicator, it will be recorded. Any variations, those, then they can able to do any adjustment to the particular gear or to the manufacturing process, so that in the future these type of fluctuations or deviation will not going to happen for the production of the gears, right? You can see over here in the image, tooth by tooth, the gear will be rotated one by one. So this plunger you can observe with the ball, it will going to sense it, then digitally or pointer moving on a scale, that value will be noted. So finally you can able to make this type of inspection for the amount of eccentricity, amount of run out in the given gear blank, tooth by tooth, right? So this is the one of the element in the given gear, right? Run out. The second element is the pitch, right? Second element will be the pitch. You can observe here in this particular image, right? See, pitch means you can observe here from this point to the this point. With respect to this line, this is the pitch for the given gear, right? See, there are two ways of measuring the pitch for the given gear blank. For the inspection of the pitch, there are two ways. One of the way is called point to point measurement. The another way is direct angular measurement. See, the first one, point to point measurement, from one point to another point. Those point is nothing but tooth point to tooth point. That is one tooth point to next tooth point. Right? That's why it is point to point. But here, the first one I represent as tooth to tooth measurement, because tooth point to next tooth point. Right? So tooth to tooth measurement or point to point measurement of the pitch for the given gear blank. What you are observing over here, this is the actually the machine which will going to measure the pitch of the given gear blank from one point to the other point. See, this machine, it consists of three tips. You can observe the cursor here. This is the sensitive tip, right? And this is the measured tip, fixed measuring tip. This is sensitive tip. This is fixed measuring tip, right? Right? So three tips: sensitive tip, fixed measured tip, and one more is there, that is adjustable or guide stop. Right? Three tip actually which come in contact with the given gear blank to measure point to point or tooth to tooth measurement. Sensitive, fixed, adjustable, or guide stop. You can observe over here on the image. Right? Right? Pitch from this point to this point. Point to point means this point. What you are observing here, the cursor, this point, the sensitive tip is there. Then one more point is this one, fixed measure tip. Right? This is just the guide tip or adjustable tip. Only from this point to this point, you're actually measuring the pitch of the given gear blank. As you can see here in this image, see the cursor from this point to this point. It is the pitch which is actually being measured. Tooth to tooth or point to point measurement. See here also there will be a dial indicator, adjustable screws. This dial indicator reading will be taken to know the any variations in the dimensions, right? See dial indicator, as you know, it is a comparator, right? All of you know dial indicator is a mechanical comparator, right? So dial indicator won't be able to give exact values. It only shows the difference. That difference means in the sense there should be some standard, right? So for that you can observe here in the sentence we're going to use the slip gauge. So there is distance between fixed and sensitive tip. So this is the sensitive tip, this is the fixed tip, is equivalent to base pitch. You can observe here this is the base pitch of the gear with the help of slip gauge. Then they will going to move it, then they are going to keep it in the place between one point to other point. So the reading will be observed on the dial. So all the three tips are contact the tooth by setting the instrument, and the reading on the dial indicator is the error in the base pitch. All the three tips are in contact: sensitive tip, fixed tip, as well as this adjustable or gauge stop, right? And the reading on the dial indicator is the error in the base pitch. Any fluctuation in the dial indicator that represent the error in the pitch for the given gear plank, because it is a comparator dial indicator, right? So that's why they are going to use this slip gauge. Then they are going to keep it on between these two points. Then they can able to measure this variations. This is one of the way in which the pitch can be measured, point to point or tooth point to tooth point measurement. Here measuring machine, gear tooth pitch measuring machine from point to point. There will be a guided stop or adjustable one, which you have seen in that video, and two tip, right, which will come in contact as it is shown in this image, pitch from this point to this point. So this is point to point measurement. Any variations, it will be shown in the dial that can be noted down. This is the one way. See the procedure here, it is like this, right? The distance between the tip 1 and tip 2 is set to standard using the slip gauge. When the dial gauge is showing the reading, considered as 0 at the beginning stage, right? Because the dial indicator is a comparator. Comparator won't provide exact dimension of the component. It does not mention the actual pitch of the given gear. It actually represents only the variation. It is doing inspection. It is not actually doing the measurement, right? Like the vernier caliper or the micrometer. It only shows the variations, as you all know, comparator, right? For that, some standard is required, and that standard is the slip gauge. What is being used in this, right? The second is next is the machine is then applied to the gear under test. All three tips are made contact to the gear under test that you observed in that video, right? Reading of dial indicator shows the variation in the pitch. Here only it shows the variation. It not shows the actual dimension or the pitch of the given gear blank. So repeat the procedure for the next pair of the tooth. So it will be repeated using this particular pitch measuring machine. So right, this is the first way. The second way of measuring the pitch of the given gear plank, direct angular measurement. As the name implies, it is direct. Directly from the dial gauge, they will take the value, right? See, basically based on the indexing. You can observe here, this is the image. Here also pitch means from this point to this point, right? Here two dial gauges are there, dial gauge A, dial gauge B. See here two dial gauges to determine tooth to tooth pitch errors. direct angular measurement. The gauge A is constant due to gear indexing. I hope all of you know indexing is about. The indexing is particularly a word. It is used in the usually in the milling machines. In machine shop lab, you will going to perform this gear tooth cutting on the given aluminium gear blank. You will going to perform this gear tooth cutting operation. While performing this gear tooth cutting operation on the milling machine in the lab, you have to perform this indexing, right? Indexing is nothing but dividing the circumference of the circular workpiece into equal spaced division. But observe that gear, even if it is having the tooth on the periphery of the gear, 25, 35 teeth, all are equi spaced. How that equal spaced tooth to tooth, it will be there on the periphery of the given gear blank. It is because of the indexing, right? So that is what the indexing is about. It is the process of evenly dividing the circumference of the circular workpiece into equal spaced division, indexing. Without indexing, you can't perform the gear tooth cutting operation for the equidistance. You can't maintain that equidistance. Then the pitch will go error from one tooth to another tooth, right? So gauge A is constant due to gear indexing. Any change in the gauge B shows that there are errors in the pitch. It is the simplest method for measuring the error by using the dial gauge against the tooth. See, in this method, a suitable point on the tooth is measured after the gear has been indexed by suitable angle. If the gear is not indexed through the angular pitch, the reading differs from the original reading. So whatever the difference will be there, that will be the error in the pitch of the given gear blank, right? So this is the another way in which you can measure the pitch of the given gear blanks. Right? So this is the pitch measurement. Second element in the given gear blank found through the inspection to base. Right. Next, third element in the given gear blank is the profile. Right. Profile checking. The profile represent here. Profile is this, right, in the given gear blank. So this is the particular machine, involute gear measuring machine, where it measures the profile for the given gear blank. You can observe here there will be plunger, right? Here dial indicator, right? This plunger we can observe in this image here, right? So this is the gear blank. One of the tooth it has been taken here as a example, right? See, in this particular method, the gear is held on the mandrel. You can observe here mandrel, and a circular disc of the same diameter as the base circle of the gear for measurement is fixed on the mandrel. So this is the mandrel. After fixing the gear in the mandrel, the straight edge of the instrument is brought in contact with the base circle of the disc. Once it made contact, the gear and the disc are rotated and the edge moves over the disc. Right? The stylus, what you are observing here, or you can consider as a plunger, it moves over the tooth profile, and any error will be there that will be showing on this pointer. If the profile is proper from one tooth to another tooth, this plunger, or you can call it the stylus, will not make any variations in this. If any variations are there, then it will make the dial indicator to move so that it represents the error which is shown on the dial gauge. So this is the profile checking. So not much of the information it is there in these, right? Only this much how it works, what the element it is, that only those things it is there, but the images it will not be there in any other. So just added these images for your reference. So without the image it will be difficult for you to understand these things, right? So this is the another element which will be inspected in the given gear blank profile checking, right? The fourth element here, it is the lead. So all of you have already know that one, what is the lead in the screw thread, right? Or here lead is what, one pitch is equal to one lead is equal to one pitch, what it represent. So one rotation it will move only the one single distance, right? That is the the more the leads, more the number of pitch it can able to travel in a single go, right? See here, you can observe here, lead checking instrument is somehow it look like this. It is the lead means the axial advancement of the gear tooth in one complete rotation, in one complete turn, right? See, the lead checking instrument are advances a probe, right? Here the probe along the tooth surface. In between these two there will be gear blank, right? This probe will advances into it to check whether the gear rotates, how much of lead it can able to rotate in one turn, right? That is what the checking of the lead. You can observe that in this particular video. So that is about the lead. The fifth element will be the backlash. I hope all of you know that one backlash is about in the gear blank. See, what do you mean by gear? What do you mean by backlash? Will it be there or it should not be there for the gear? When the two gears are mesh, whether the backlash should be there or not? Backlash, theoretically, presence of the backlash may lead to a decrease in the efficiency, right? But practically, if there is no backlash at all, there is no free movement for the two gears while doing the mesh. You can observe here in this image, backlash it is represented here, right? I think you already know this one, backlash, right? In the kinematics of machines also you studied this, right? Backlash. So it is the distance through which the gear can be rotated to bring its non-working flank in contact with the teeth of the meeting gear. We can consider it as a little bit of gap, or this tooth will not come in contact. That gap will be considered as the backlash. Some in practical, some backlash should be there so that you can able to have the relative movement. If there is no backlash at all, then it will be fixed. It won't able to make the rotation with respect to another gear element, right? See, there are two types of backlash: circumferential one and the normal backlash. See, this is the way in which the backlash for the gears during the meshing will be inspected. Here also they will use the dial indicator. Dial indicator is a comparator. It does not measure the actual dimension, but the variations or differences it will going to show as compared to the previous one, right? You can observe here, right? This is the gear and this is the other one, right? The tip of the dial indicator on one tooth, one will be held, right? One of the two gears of the pair is locked while other one is rotated forward and backward. Assume this pinion gear will be fixed, right? It will not move. Only this gear will going to be moved front and backward. And by using this comparator, there is a dial indicator. The displacement is measured, the gap. Suppose, listen. So this gear, if it is fixed and only this gear is moved front and back, you can able to observe the variation. this gap. That is what the backlash is about, right? The stylus of this particular comparator is locked near the reference cylinder, and the tangent to this, it is the circular backlash, right? So there is all a backlash in the particular gear will be inspected. This is another element in the gear blank. See here also a small video is there how to check that particular backlash in the given gear. How much of backlash will be there? It will be shown in the this particular comparator dial indicator, right? This is the another element that will be inspected. Backlash. The sixth element is the tooth thickness measurement. So all of you know that one, tooth thickness measurement. The previous classes we discussed about these three methods, right? Tooth thickness by using gear tooth vernier caliper method. It is also called caudal thickness method, base tangent method, constant chord method. So these methods we discussed already about. This is also comes under the inspection of the gear. Right? Usually the tooth thickness will be measured at the pitch circle. And in most of the cases, the caudal thickness measured is carried out, right? This gear tooth vernier caliper. Depending on the requirement, based on the functionality of it, whether the base tangent method or the constant caudal method will be used to do this type of inspection. That is tooth thickness. For all the three, we discussed and we get into that equation how to measure that the width as well as the depth for the given tooth, right? So that is comes under this sixth element, tooth thickness measurement. It is important. You might have seen in the question paper, VTU question paper, multiple times it is being asked that we will going to discuss later about the questions, right? The seventh one, the last one is measurement of concentricity. The first one is run out. The first element, it is eccentricity. This is concentricity. The seventh element, what we are discussing now with respect to the given gear blank, it is the concentricity. You can observe in this image concentricity, right? That is the center in which the gear is mounted should be coincide with the center from which the gear is generated. Concentric circles, concentricity, right? It is easy to check the concentricity of the gear by mounting the gear between the centers and the measuring the variations between the successive teeth, right? Any variations, that is any eccentricity will be present, it will be noted. It is called the concentricity, right? The from the center with respect to the another center, how it's going to rotate, which is mounted on the particular center. That is the concentricity. So these are the 7 elements which will be inspected in the given gear blank. Right? So run out, pitch, profile, lead, backlash, tooth thickness. In the 3 methods we discussed already, tooth thickness. Then the last one is the concentricity. Right? So these are the various elements in gear inspection. Right? So next topic, it is Parkinson's gear tester, or it is also called rolling gear tester. Parkinson gear tester. You can observe on the screen, the right side, this is actually the measuring machine which will inspect the gear, which will test the gear. This particular machine, it reveals these elements, the form of the tooth, the pitch, concentricity in the given gear blank. You can observe here gears, right? So this is the gear tester. Generally it is called gear tester or rolling gear tester or Parkinson gear tester. See here, this is the The diagram for this Parkinson gear tester. See here, you can observe this is the master gear, or you can call it as the standard gear. In order to test a component, you need to have some standard, some master, and this is the what the master gear. With reference to this master gear, they will check this another gear. We can observe here gear under test. This is the gear which is will be inspecting as of now, and this is the master gear, or you can consider as a standard gear. By meshing these two, they will do the testing for the given gear blank for these element, for the pitch, concentricity, the form of the tooth, those elements. Right? You can observe here, this is the floating carriage, right, on which actually the gear will be mounted. This is the gear which will be inspecting, and this is the master gear. This is on the fixed adjustable carriage. This is the floating carriage, and it is connected to a dial indicator. The dial indicator will show the variations when it having the uh, when it assemble, or when it's going to have the meshing with the master gear, right? So this is what the center distance. So consider this is the master gear, and this is yellow color one will be the gear which need to be inspected. It will go to mesh like this. Any variation will be there. This particular gear which is going to be inspecting, it will be pushed away, right? And that will be indicated in the dial indicator. You can observe here, this is the calibrated spring. This is the one which maintains the pressure, the meshing pressure between this and this gear. So any variations, it will push. Then there will be plunger. The dial indicator will going to show the variations for the gear which is going to be inspected. Right? See, this is how the image you can able to observe. Master gear is here. This is the gear which is under test, and the plunger of it connected to the gear which is under test, and this dial indicator, what you are observing here, it will show the differences or deflections. They can use the graph also to plot and to know any variations in the given particular gear blank as compared to the master gear or standard gear. See this, as the master gear rotates, right, when it is being meshing with the gear which is need to be inspected, which is under a pressure by this calibrated spring. The movement of the sliding carriage are indicated by the dial indicator. Any variations during this meshing, if it is being noted, that variation will be indicated in the dial indicator, right? You can observe here the conditions. If it is having this type of particular plot, the gear is fully satisfactory. This is moderate, this is unsatisfactory. And this is the cut section view of this particular Parkinson gear tester. Calibrated spring. This is floating. This is fixed one. This is master gear, and this is the gear which is in inspection. And this is the center distance from one to other. This red arrow mark indicate the movement. Any variation, it will push it. It will make the differences, and that will be indicated in the dial indicator. What it is being shown over here, it is like a manual one. Because designing the dial indicator, the person will going to note it any variation in the given gear test. But during the mass productions of these gears, it can be automated also. Gear tester or rolling gear tester to test the given gear blank. Automatic, right? By comparing with the master gear or standard gear, it inspects the tooth to tooth or point to point, the pitch, concentricity, run out, those things it can able to measure, right? So working, as I told, that one using the dial gauge. That is, if it is in the manual, if you are doing, if it is with respect to automated one, it will be having the software for it to record the each value of it. So some of the limitations we'll discuss now. Limitations of this particular Parkinson gain tester is friction in floating carriage reduces sensitivity. Some of the drawbacks of this, it will be friction in the floating carriage reduces sensitivity. It is not suitable for the gear which is having the diameter more than 300 diameter. But I've observed in that video also, right? It is not bigger the diameter gear blank will be inspected, right? Because those things will not be suitable. So measurement are directly depend on the master gear. But I've observed in those video also, in the image also, it depends everything on the master gear, right? Or standard gear. Everything is dependent on this. With respect to master gear or the standard gear only, it will going to give the result in terms of whether it is accepted or it is having any errors in it. The error in the pitch, helix and tooth thickness are not clearly identified. It will be inspected, but to that level of accuracy, because all the elements is inspecting in a one go, they will be not be identified as clearly as required, because all the elements are inspecting in a one go, right? Those are some of the limitations of this Parkinson gear tester, or it is also called roller gear tester, right? And this is the last topic, right? This is coordinate measuring machine, CMM, coordinate measuring machine. As the name implies, it is used for measuring with respect to the coordinates for the given gear blank of different sizes or thickness of the different varieties of the gear, can able to do the measurement, right? With respect to the coordinates, so it measures actually the geometry of the physical object by sensing the discrete points on the surface of the object. And in order to do so, to measure the object on the surface by sensing, it going to uses the probe for it. You can observe here, this is the probe, right? There will be a rod and this will be the probe. It is like a small ball which comes in contact with the surface of the object. There are different types of probe that can be used in this particular coordinate measuring machine. You can observe here in this image different varieties or types of probe we're going to use. It can be mechanical one, optical one. It can be of the different other elements also, depending on the type of gear, type of functionality what it is been using for inspecting or for measuring the gear. They're going to use that particular probe, and this is what the machine, point measuring machine, and this is what it actually look like, right? This is a diagram. So basically this is the granite surface plate what you are observing here also, because it has to withstand that bigger diameter gear blank which has to place over this granite surface, right? And this is actually the place in which the probe will be connected. What you are observing the probe here, it will be connected actually at this point, right? The x, y and z direction it can able to move. There will be a controller which can able to control the movement of this probe as accurately as possible, because the probe has to just come in contact with the surface. It is very sensible one. It very sensitively measures the surface, right? You can observe here in this particular screen, the person he is inspecting the a component here by using this particular CMM, coordinate measuring machine. There are varieties of varieties of the CMM is available. So some examples I will going to show over here. Right? So this is actually the probe which is connected to the stylus. right? Actually having this displacement transducer. It converts this mechanical into electrical signals, right? As you see over here, these type of machines will provide the precise measurement of the objects for testing purpose or for inspecting purpose or for doing any of the even the reverse engineering of the objects also done by using this particular CMM, coordinate measuring machine. It comprises of four main elements. One is, you can observe the machine itself, then the probe. There is another element, the control system and the software. These are the four elements. This CMM mainly it consists of a wide range of different sizes and different designs of probe will be available, which can be used for the measurement purpose or for inspection purpose. So these things can move in the X, Y and Z directions. See, it can be manually controlled or it can be even the CNC, computer numerical controlled also, right? See, none of the CMM, it's going to have the different probe connected on one particular probe itself, so that it can able to have the interchanging whenever it is required. CNC, computer numerical control. Here only one probe it is being used, which is actually inspecting. Even for the reverse engineering of the component, it can be used, right? So I'll play a video to show you about this.